In this lesson, we'll be looking to see how to transform the parent graphs of trigonometric functions. So we'll call this 6,3 to 6,6. And this is called transformations of trigonometric functions. So remember, the first most important thing in math is factoring. The second most important thing in math is how to transform graphs. Speaking of transformations, let's just recall our basics, that whenever we have a function, say f of x, we could do 4 different things to it. So let's look at an absolute value function. We'll put a number here, here, x, c, and d. Now c and d move the graph. They translate the graph. So if d is positive, we're going up, negative goes down. C, we go left and right, depending on if it's positive or negative. And A and B are going to stretch and shrink the graph. If they're negative, so let's say if the absolute value, or let's say if A is less than 0, it reflects over the x-axis. And if B is less than 0, it reflects over the y-axis. If the absolute value of A is bigger than 1, similar to if the absolute value of B is bigger than 1, the graph is going to get narrower. But if it's on the outside, this is called a vertical stretch. If it's on the inside, this is called a horizontal shrink. Our trigonometric functions are going to have both A and B values. The B is going to affect the period, so it's going to compress the graph or stretch it out. And both of these actions tend to make the graph narrower. Now if the absolute value of A is less than 1, this is called a vertical shrink. And if the absolute value of B is less than 1, this is called a horizontal stretch. Both of these actions make the graph appear wider. Now let's take a look at how this affects trig functions. We're going to have y is equal to a times the trig function. We'll just use sine for these purposes, with a k value, and then theta plus the phase shift, and then plus the vertical translation. Now, the absolute value of A is going to give us the amplitude of the graph. And remember, the only graphs with amplitude are sine and cosine, so we'll say sine of theta and cosine theta only. In order to get the period, we're going to take the normal period of our trig function divided by k, and that's going to equal our period. Just make sure that we factor out k. PS stands for our phase shift. And phase shift moves the graph left and right. Positive goes left, negative it goes right. And then VT stands for our vertical translation. That just means translation up and down. If it's positive, it goes up, negative, it goes down. So now let's take a look at 4 graphs. What we are going to do is find the amplitude, period, and phase shift, and then we'll practice graphing them. So let's take a look at, let's see here. We'll write out the directions to state the amplitude. Period and phase shift. And then we'll graph from, let's say, negative 360 to positive 360, or from negative 2 pi to 2 pi. Sometimes people don't know, like, when do you use degrees, when do you use radians. Just so you know, theta generally means we're in degrees, and if you see x, that means we have to convert to radians. It's not harder, just like with fractions and decimals. One's not harder, it's just you should be able to convert. And remember, the way that we convert is we use pi over 180 if you want radians, and 180 degrees over pi if we want degrees. Okay, so let's get started. Say we have the equation y is equal to 2 times the sine of 2 theta plus 90 degrees. Okay, well, one thing I just want to mention is this right here. Remember, if we had a horizontal dilation, we always factored out the number in front of x, like right here. Remember how we always factored this out? That's really important with trig functions. So if you have a number in front of theta or in front of x, we have to factor it out. So we'll factor out the 2. So we have 2 times the sine of 2 theta plus 45 degrees, because remember, you're dividing out 2 from everything inside the parentheses. So now let's talk about our amplitude, period, and phase shift. The amplitude would be the absolute value of 2, or 2. So I'm going to set up my graph. I'll try to make a straight line here. So the amplitude is 2, so it's going to go up to 2 and down to negative 2. Okay, how often does it repeat? Well, the normal period of sine graph in degrees is 360, and we're dividing by our k value. So this graph is going to repeat every 180 degrees. The phase shift is to the left, 45 degrees. Whenever you talk about phase shift, it has to have both of those components. So now let's figure out how to graph it. We have a general idea of what it should look like. I'm going to recommend you use your calculator and pick some values, and then we'll plot them, making sure it matches what our expectations are for the graph. So I'll do 0, 90, 180, 270, and I'm going to store those on my calculator, making sure my calculator is in degree mode. We'll plot those points, and then we'll talk. So I'm going to store 0. So 0, store for A. And then I'm going to type 2 times the sine of 2 mem variable A plus 90. Hit enter. My calculator is telling me 2. Now I'm going to do the same thing for 90. I'm just going to store 90 for A. Go back up, ask my calculator, plug it back in. I'm getting negative 2 at 90. Let's try 180. And it's 2 because the period was 180, right? So it would make sense that it is the same thing. I see a pattern, so I don't even have to plug in all of these points. Circular functions or trigonometric functions are fun to graph because they repeat. We know the graph is a wave. This is what the graph would look like, something like this. All right, so everyone could do that. That's not a big deal. What about y is equal to -1/3 times the cosine of theta over 2 minus 180? First thing let's do is we'll factor out theta over 2. So remember, when you divide by 2, that's the same thing as multiplying by 1/2. So for some people, it might be easier to write as 1/2. And then if we take that out, sorry, I was talking about 1/2 and I wrote it in the wrong place. We get theta minus 360, like that. So let's talk about our amplitude, period, and phase shift. Amplitude would be the absolute value of -1/3, which is 1/3. So I'm going to set up my graph. And the highest it's going to go is 0.3, -0.3, and we have 1, 2, 4, 1, 2, 3, 4. And let's figure out the period. We're going to take the normal period of cosine, which is 360, and divide it by 1/2, which gives us 720 degrees. So this is going to be stretched out. And the phase shift, the graph is going to look like it moved to the right 360 degrees. Whenever you pick points into your calculator, I always recommend that we use the original. So just like we did before, I'll make a table for theta, and I'll plug in -1/3 times the cosine of a divided by 2 minus 180. And I'll just pick some points here. If we could see a pattern, we don't have to keep plugging in points. So I'll store 0 for a, type in -1 divided by 3, cosine, then variable a divided by 2 minus 180. My calculator is telling me it's 1/3. Then I'm going to store 90. My calculator is telling me it is 0.2. Store 180. My calculator is telling me it's 0. 270. I'm getting -0.2. 360. I'm getting -1/3. All right. We could always plug in smaller values. You could use 45s if you want. But at 0, it hits our amplitude. 90, it's a little lower. 180, it's 0. Then -0.2. Looks like the graph's kind of going like this. It's climbing. It's our top point. And then I would imagine it would do the same thing coming back down. Because cosine is a wave, that's what I would expect. And you could always plug in points. Plug in -180, you will see that it's 0. And the period is 720, which is exactly how long that distance is. The period is 720 degrees. So we'll do a couple more in radians, and then I wanted to go over a supplemental worksheet just to make sure you understand how to do this. So what if we had y is equal to 1/2 of sine of pi over 2 and then x. So this is in radians. So technically, I mean, we could factor out the pi over 2 like this. The amplitude is just 1/2. The absolute value of 1/2 is 1/2. So when I go to graph this, I am going to be in radians. The highest we're going to go is 0.5. The lowest we're going to go is -0.5. We have 1 pi over 2, 2 pi over 2, 3 pi over 2, and 4 pi over 2. Now let's go to our period. The way we figure out our period is we take the normal period of sine and divide it by k. Now k is the number in front of x. So what is 2 pi divided by pi over 2? Or 2 pi times 2 over pi. Pi's cancel. It looks like this repeats every 4 radians. Okay, so it's a little bit hard to figure out on our graph. I mean, 4 radians, 3.14 radians is pi, right? 4 radians, it's going to be stretched out a little bit longer than pi. And our phase shift, it doesn't move left to right because there's no plus or minus inside of the parentheses. So we could just say none or 0 degrees. Let's plot some points here. Because we are in radians, we'll use x. Now your calculator, you have to make sure you're in radian mode. So if you got a calculator, I recommend that you just hit the DRG button, go over to rad for radians and hit enter. And I'm going to type in 0.5 sine parentheses. I'm going to type in pi divided by 2 and then a. That's how I'm going to type this in. And what I'll do is I'll start at 0, then I'll store pi over 2, then I'll store pi, 3 pi over 2. We'll see if we can figure out some kind of pattern here. So 0.5 times the sine of pi divided by 2 times mem variable a. And I'm going to start at 0. So at 0, we have 0. There's no phase shift, so that's where sine usually starts. At pi over 2, I'm going to store for a. Just typing in pi over 2, go for a. And I'm going to go back, and my calculator's telling me this is 0.3. 0.3 is 0.4, 0.3, 0.2, 0.1. 1, 2, 3, 4. So 0.3 is like right here. The highest it goes is 1/2, so we still have to get up there. I'm going to store pi, and I get negative 0.48. All right, or 0.49. I'm going to type in 3 pi over 2, store it, and I'm getting 0.4. And let's try 2 pi. And I'm getting negative 0.2. Okay, so remember, this is going to stretch out over 4 radians. So it's going to be a little bit more than pi radians. So I would imagine the graph looks something like this. Something like that. This would be pi radians is 3.14. So right here would be about, if this is 3.14, right here would be about 4. And then the pattern would continue. So it looks something like that. All right, if you want, we could try the negative values and just see if our shape makes sense. So for negative pi over 2, store for a, we get negative 0.3. For negative pi, I'm getting 0.4, 0.5 almost, 0.49. And then for negative 3 pi over 2, I'm getting negative 0.4. Oops. And then for negative 2 pi, I'm getting 0.2. So we can keep this pattern going. Let me just see what's happening at negative pi over 4. I'm getting negative 0.5. So it looks like the graph looks something like this. Roughly like that. All right, I tried negative 0.4 just to get an idea if the graph went like this. So negative 0.4 was negative 0.5, so that gives us a more clear idea. Let's try one more of these and then we'll go to a worksheet. Let's say y is equal to pi times the cosine of pi x. The amplitude would be the absolute value of pi, or just pi. So I'm going to set up my graph. 1, 2, 3, 4. The highest it goes is pi, so the lowest it goes is negative pi. We'll go maybe 1, 2, 3, 1, 2, 3, 1, 2, 3, 4. And we'll try the period. The way we get the period is we take the normal period, which is 2 pi, and we divide it by the number in front of x. So this is going to repeat every 2 radians, and there's no phase shift. So we could just say none or 0 degrees. Okay, so now let's make our table. Our calculator should be in radian mode, and I'm going to type in pi times the cosine of pi a, like that. Let's see if we can figure out a pattern. Okay, so pi times the cosine of pi mem variable a. I'm going to store 0. And my calculator is telling me it's 3.14. Okay, that's great. So right at 0, it's pi. And the period is every 2 radians. So I'd imagine it's going to be over here. 3 pi over 2 is about 4.7, so it's going to be maybe like over here. And we can see a pattern, right? If it's every 2 radians, it's going to be something like this. Just going every 2 radians. It's going to be something like that. All right, so this is pi radians, right? So that's 3.14. 3 pi over 2 is 4.7, so that's why I have that dot a little bit before that. And then 6, this would be 6 point whatever, so I'll put a dot a little bit before that. Let's try pi over 2. Pi over 2, store it, and I'm getting 0.7. Okay, let's try pi. Pi, I'm getting negative 2.8. 3 pi over 2. I'm getting negative 2. And 2 pi, I'm getting 2. Right here. All right, so let's connect the dots. And I think it'll look something like this. It doesn't have to be perfect, but that's what the graph would look something like. Now, we could do the same thing on the other side. We'll just kind of draw a rough sketch here. Something like that would be fine. All right, so that's how we graph trig functions, sine and cosine. Let's take a look at some other ones from a worksheet. All right, now this could be found in the supplemental materials. And let's take a look. So first three are in degree mode, and the last three are in radians. So to get started, the amplitude for the first one just be 1. There's nothing in front of theta, so our period is normal 360. And our phase shift would be 180 degrees to the right. I'm going to make a table. I'll just plug these right into my calculator, and then I'll plot them. So I have to change my mode back into degree mode, and I'm going to start at 0. So I'll store 0 for A, and I'll type in sine mem variable A minus 180. And I'm getting 0. The period is 360. So 360 before and after, I'm going to put the same value. 90, I'll store it. And you can see I'm just picking points. If the period is 360, that means that this will be -1, 360 before. At 180, I'm getting 0, and it's probably going to be 1. So we could see the graph would look something like this. That's what that graph looks like. Let's graph tangent. So even though there's a 3 in front, it's important that you write none for the amplitude. Don't put 0, that's not correct. Just like undefined means undefined, nothing else is acceptable. For amplitude, if it's not a wave function, you have to put none. There's nothing in front of theta, so our period is still 180 degrees, and our phase shift is going to be to the right 90 degrees. So now let's pick some points here. I'm going to type in 3 times the tangent of A minus 90. And I'm going to store 0. And I'm getting a domain error. So this is undefined. 180 degrees, it'll also be undefined. 180 degrees, it'll be undefined. And now let's figure out what's going on in the middle. I'm going to store 90. And I'm getting 0. What's going on at 135? Store that. Now it looks like it's 3. And our graph is starting to take shape here. We know what the graph of tangent looks like, so we could just kind of fill in the middle. All right, so now let's move on to the next one. Even though there's pi, we're still in degrees. And let's go ahead and figure this out. So let's see here. The amplitude. Well, first let's factor out this 2. So we're going to have y is equal to negative pi times the cosine of 2 theta plus 22.5 degrees. The amplitude would be the absolute value of negative pi, which is pi, or 3.14. So I'd expect the graph to go up to here and down to here. Something like that. Okay, now as far as the period, the normal period of cosine is 360. Divided by 2 is 180, so it'll repeat every 180 degrees. And then our phase shift is going to be 22.5 degrees to the left. So I'll type the original into my calculator. You always use the original to get your points. So negative pi times the cosine of 2 mem variable a plus 45. And I'll plug in 0 first. So if you plug in 0, you'd get negative 2.222, something like this. The period's 180, so 180 degrees before and after, it's going to be the same thing. So now let's try 90 degrees. 90 degrees is 2.22, all right? So 180 degrees before and after. Looks something like that. And 22 degrees to the left is our phase shift. So our graph, normally cosine looks like, so it's flipped upside down. Usually cosine looks like this, right? But because it's flipped upside down, it'll look like this. If it's moved 22.5 degrees to the left, it'll look like that and then stretched out. So I would expect at negative 22.5 degrees, it'll be pi. Let's see if that's what happens. Negative 22.5, I'll store for a, and I do get negative pi. So right here, this is negative 22.5. It's negative pi. Come up, go down. So you could kind of see the graph hits the amplitude a little bit before those points. And it's not the prettiest. Something like that. All right, so that's how you would graph those. Let's move to radians. Make sure your calculator's in radian mode. All right. And let's take a look. So to get started here, cotangent, well, we don't have a button for cotangent. So what I'm going to do is I'll figure out what tangent of x minus pi over 2 is, and then I'll take the reciprocal, because cotangent is the reciprocal of tangent. So let's try this out. I'm going to type in the tangent of mem variable a minus pi over 2, and we'll start with 0. If we plug 0 in, we get an error, meaning it's undefined. If we try pi over 2, I'm seeing that we get 0. If we try pi, I'm seeing that, let me see here, pi store for a. I'm seeing that we get an undefined again, and it looks like this pattern is going to continue. The reciprocal of undefined is 0. The reciprocal of 0 is undefined. So you could see how I'm using tangent to graph cotangent. Remember that cotangent has no amplitude. The period of cotangent is 180 degrees, or pi radians, and we're going to the right, pi over 2 radians. So let's go ahead and graph it. At 0, the reciprocal would be 0, and if the period is pi, pi later and before would look like that. Pi over 2 would be undefined, so I think we're starting to see what this graph would look like. Now just remember, cotangent is almost like a cubic function. It just is reflected over. So this is what this graph would look like. something like that. Okay, 2 more to go. Now this next one is using cosecant. So we're going to have to do a little bit of work to get started. First thing let's do is let's divide both sides by 2. So we get y is equal to negative 2 times the cosecant of x over 2 plus pi over 2. And then let's factor out the number in front of x. And pi over 2 divided by 1/2 would just be pi. You can even do it off on the side if you want. Pi over 2 divided by 1/2 is the same thing as pi over 2 times 2 over 1. These would cancel, giving you just pi like we said. Okay, so let's take a look at this. The amplitude for anything that's not sine or cosine is none. The period, well, normal period of cosecant is 2 pi. But if you divide that by 1/2, then you would get 4 pi. The phase shift, once we have the 1/2 factored out, it's easy to see our phase shift goes to the left, pi radians. And now we're ready to plug in values. But you have to be careful. We're going to use this to plug in our values, and we'll use secant to figure out what the graph of cosecant looks like. So on our calculator, this is what we're going to type in. Let's type in, I'm sorry, I think I said secant. We'll be using sine to figure this out. Let's type in sine of 1/2 a plus pi over 2. And then the way we're going to convert that to our actual graph is we're going to figure out what 2 times the reciprocal of that is. We're not taking the reciprocal of 2, we're taking the reciprocal of sine to give us cosecant. So let's see what happens. Okay, so I'm going to type in sine of 0.5 mem variable a plus pi over 2. And I'm getting 0. Well, let's pick a number here. So at 0, my graph is 1. So 2 times the reciprocal of 1 is 2. Let's try pi over 2 now. Pi over 2, I'm going to store it for a. I'm getting 0.7. So 2 times 1 over 0.7 is 2.8. Let's try pi now. Pi store for a is, I have a little bit of trouble here. Let's see. Pi store for a. I'll go back to my equation with sine. And that would be 0. So 2 times the reciprocal would give us an undefined answer. Starting to see what's going on here. Now let's try 3 pi divided by 2. We'll store that for a. And I'm getting negative 0.7. So I'm going to type in 2 times 1 over that answer, and I'm getting negative 2.8. So let's see if we could piece this together. At 0, 2 times the reciprocal was 2. Pi over 2, we were at 2.8, and then pi was undefined. At 3 pi over 2, we were negative 2.8. I'd imagine this would be negative 2, right? Because we know what the shape of cosecant looks like. We could start figuring out the pattern of the graph. Negative 2.8, negative 2, something like that. Cosecant, remember, looked like a parabola. Alternating parabolas. Okay, and that's what we get. So now let's take a look at number 6. So for number 6, we have secant, and we are going to be using the reciprocal of cosine to figure out secant. So let's figure this out here. We'll start with an x. We'll figure out what the cosine of 4x plus 2 pi is, and then we'll figure out the reciprocal. All right, so let's go ahead and get set up. And the amplitude, because it's not a wave graph, is going to be none. To figure out our period and phase shift, we have to factor out a 4. Two pi divided by 4 is just pi over 2. So our period is normally 2 pi, but we're dividing it by 4. So our period here would be pi over 2. So every 90 degrees, it's going to give us a full cycle of the graph. The phase shift is going to be to the left, pi over 2. And let's go ahead and type this into our calculator and see what happens. So I'm going to type in, first we'll start at 0, we'll store it, and I'll type in cosine of 4, mem variable a, plus 2 pi. At 0, I'm getting 1. The reciprocal of 1 is 1. We'll start right here. Now remember, the period's pi over 2, so it's going to be 1 here, here. Every pi over 2, it's going to be the same exact thing. It's going to repeat every pi over 2. All right, now let's try, well, pi over 2, I know it's going to be 1. You could double check it. Let's store pi over 2. Yeah, it's going to be 1. It's exactly the same thing. So let's pick another number. How about pi over 4? That's in between 0 and pi over 2. So I'm going to store pi over 4, store for a, go back, and my calculator's telling me -1. So in between, we're at -1. Now this is going to be a little crammed. So what's going to happen is we're going to have a parabola, and then an upside down parabola. A parabola, and this is what the graph's going to look like. It's not the prettiest thing in the world, but this graph does have a period of pi over 2, and it looks exactly the way it's supposed to look. So I hope this helps you feel more comfortable with graphing trigonometric functions as well as regular functions by practicing the transformations. Please stay tuned for our next lesson.